Hello everyone, I'm Fabiane from the Bendable Electronics and Sensing Technologies Group from the University of Glasgow in Scotland, and today I'll be presenting our work on screen-printed flexible carbon versus silver electrodes for electrochemical sensors. Here is the outline for today's presentation. I'll be introducing silver and carbon screen-printed electrodes, mainly in the topic of electrochemical analysis in water, and then I'll go over how we fabricated our electrodes, the electrochemical characterization in saline solutions, and what we have planned for future studies. First of all, I'd like to take a step back and analyze the common setup used in laboratories for electrochemical studies. The setup usually involves an electrochemical cell with a 3-electrode setup. A working electrode, where the electrochemical event of interest occurs, a counter-electrode, which is a high surface area inert electrode used to complete the circuit for current flow, and a reference electrode, an electrode that has a stable potential that is used as a reference point. For now, I'll focus on the working electrode. Common materials are carbon, gold, and platinum electrodes, with the most important aspect being their inertness at a potential window of interest. However, silver can also be used as an active working electrode, for example, in electroplating, because silver is quite reactive. One thing that is interesting to notice is the electrodes are quite well protected with inert materials as to make sure there is little to no interference in the experiments. However, this can be a bit different when it comes to printed electrodes. With printed electrodes, the idea is to mimic the laboratory setup with a cost-effective fabrication technique. Here you can see some commercially available electrodes, with metal ones designed for a 3-electrode setup and ALS ones for a 4-electrode setup. But what is interesting to see is the range of materials available, where carbon is not necessarily the most used choice anymore. Although metals working electrodes tend to be an inert material such as carbon, the conductive track is made of silver. Printed electrodes give the opportunity to quickly test new materials. However, depending on the medium that they're going to be used in and what is the desired application, different challenges arise. One of the possible applications for printed electrodes is routine environmental analysis, for example, in heavy metal, inorganic nitrogen, and pesticide detection. The choice of material for the conductive path is essential for a reliable ion-electron transfer, and as mentioned before, it is of great importance for a successful electrochemical analysis. Water bodies are a complex mixture of different salts and ions, and the right electrode material can minimize cross-interference. Even when used only as a conductive track, the material of choice might interfere with the sensor response if not well insulated. When dealing with water bodies, we should also consider the environmentally friendliness of the electrodes. Materials that are toxic to aquatic life or human consumption should be avoided whenever possible. In this context, silver and carbon seem to be popular choices, however, they have quite different properties. Silver seems to be a popular choice due to its high conductivity and lower cost when compared to other metals. But chemically, silver is a reactive material. It is known to form salts with elements from the halogen family, and when we look at seawater composition, we can notice a high concentration of such elements. Particularly, chlorine can be a problem. Silver also easily oxidizes. Therefore, in some cases, an alternative conductive track could be more advantageous. There are, however, many other criteria to consider, as paste cost and composition, electrode degradation, toxicity, and so on. In this context, it seems carbon could be considered as a more suitable low-cost option. But commercial carbon inks tend to have a higher resistance, which can hinder some experiments. Therefore, some compromises might need to be taken. In this paper, we wanted to focus on all silver and all carbon electrodes, as it's important to understand how the choice of electrode material can affect the experiments, ranging from their electroresistance to electrochemical properties. We chose screen printing as our fabrication technique due to its direct, easy fabrication steps. We used PVC as the substrate to offer some flexibility and used commercial pastes. The sheet resistivity was much lower in the silver paste, however both values were acceptable. The pastes were dried at 80 degrees Celsius for 20 minutes and 2 different designs were used. The strip was used for cyclic voltammetry and differential pulse voltammetry studies, together with commercial reference and counter electrodes, while the interdigitated structure was employed in the electrochemical impedance spectroscopy study. To minimize interference, we decided to use the same carbon paste on the electrical connection of the carbon electrode. In this slide, I'll go over some of the basics of electrochemistry to understand how the electrode's materials choice can affect the experiment. Cyclic voltammetry is a popular electrochemical technique. It gives information about the reduction and oxidation of species near the working electrode surface, and it can also be used to study electron transfer-initiated reactions. We can see a representation of a CV voltammogram on the left figure, with clear redox peaks. However, faradaic processes are not the only reaction that can happen in an electrochemical experiment. Non-faradaic processes can occur in the form of a double layer formation, which, as the name suggests, is constituted of two layers. An inner layer of molecules is specifically adsorbed at the electrode, and a diffuse layer. This double layer is unique to each experiment setup. The reason the double layer is such an important phenomenon in electrochemistry is because it significantly affects the measurements. If the electrochemical cell is represented as a circuit, the double layer structure can be viewed as a capacitor. Therefore, to obtain the desired potential at the working electrode, first, the double layer must be charged, creating a capacitive current that flows in the electrical circuit. Since this current is not correlated to the reduction or oxidation of the analyte or substrate, it often interferes with the results of the electrochemical experiments. This could be a problem when the non-faradaic current is much larger than the faradaic current, and that is the reason why inert electrodes are usually preferred. So let's analyze the voltammetry experiments for the silver and carbon electrodes. We chose two common salts for our experiments, sodium chloride and sodium nitrate. All studies were performed under nitrogen atmosphere. The observed current density level for the silver electrodes was almost 100 times higher than as compared to the carbon ones. This could be due to the high conductivity of the silver electrode and the faradaic reaction of the electrode with the solution. In Figure A, we can observe that the presence of salt seems to influence the silver electrode response current. The current density increased with the conductivity of the solution by increasing salt concentration, and it is more significant in the silver electrode than in the carbon electrode. Even at different concentrations of silver nitrate and silver chloride, carbon appears to stay mostly inert, while the silver electrode clearly shows similar cathodic peaks at around minus 0.5 volt for both salts. To better analyze faradaic currents, differential pulse voltammetry was employed. DPV is a highly sensitive technique that improves the signal-to-noise ratio of the voltammogram. The capacitive or background current is nearly eliminated by allowing sufficient decay of the non-faradaic current. By analyzing the left figure, we can see most of the cathodic peak seems to come from non-faradaic reactions, as the DPV shows almost no redox peak from minus 0.8 to 0 volts for silver. A possible explanation is the occurrence of an enhanced pseudocapacitance on the surface of the silver electrode in the presence of salts, which can be better understood by the electrochemical impedance spectroscopy studies. EIS is one of the most complex techniques in electrochemistry. The data can be analyzed in terms of an equivalent electrical circuit to reflect the reality of the system as close as possible. More specifically, when an electrode is in contact with the electrolyte, the Randall circuit is normally implemented, which can be seen on the figure on the left. With this, we can better understand the system and have information on the double layer. When analyzing the Nyquist plot for the silver and carbon electrodes, the carbon electrodes showed high ionic diffusion resistance in the low frequency range. In fact, more than 50 times higher when compared to the silver electrodes. This could be due to the high resistance of the carbon electrode and the charge accumulation on the surface of the electrode due to the double layer formation. Meanwhile, the silver electrodes offer high conductivity and charge accumulation due to the enhanced non-faradaic reactions on the electrode. Further studies were carried out by increasing the concentration of both salts. Figure A shows that the charge transfer resistance offered by the silver electrode, which corresponds to the high semicircle and medium frequency range, decreased with increasing concentration of salt. However, as compared to the sodium chloride variation, the resistance due to the sodium nitrate is less. This could be due to the influence of the chloride ions in the solution, which reacted with the silver electrode, but further studies are needed to confirm this. For carbon electrodes, the charge transfer resistance decreased with increasing concentration of solution as well. However, a higher overall resistance was observed. It could be due to more ions being involved in the electrochemical double layer formation, effectively increasing the capacitance of the electrode. Similar performance was observed for both salts, both the nitrate and chloride solutions. This showed the stable performance of carbon electrodes when salt is present in the solution. In conclusion, from the experiments we could see carbon does seem to be more inert than silver, although the proper mechanism for the interaction of silver with the salt solution still needs to be investigated. For future experiments, we'll study the electrodes' reactions under normal atmosphere and expand results to other ions, as sulfate, magnesium, calcium, and test the electrodes in real water samples. We also plan to increase the salinity concentration range. Therefore, both electrode materials have their advantages. However, all carbon electrodes could bring new features to screen-printed electrodes, such as environmentally friendly and cheaper overall cost. To increase its conductivity, solutions such as adding graphene or carbon nanotubes could be used. Therefore, it is important to understand where the electrode will be employed and which technique will be implemented to make sure it won't interfere with the results. I'd like to thank you for watching this presentation, for Flaps for giving me this opportunity, and for the University of Glasgow and Invest Group for helping me with my research, and finally, the European Union for funding the project I am part of, which is called Aquasense. If you wish to contact us, here are our emails. You can also check our social media to get updates on our research. Thank you once again.